Okay, so as promised, we are coming to phase noise in today's class. Okay, now just couple of things from last class. I think. Okay, one of them, I mentioned that the KVCO is F2 minus F1 by delta Vc. That is true if the VCO tuning was perfectly linear. Otherwise, you would give it as dF by dVc. Okay, so it's just the slope of, I think I mentioned that it's the slope of the curve, but the actual definition is dF by dVc. So in other words, sorry, at what? Yeah, of course. So it looks something like this. Could look something like this. Okay, or maybe, I mean, this it may have a broader curve. It depends. So what you want is probably something like this. Okay, you want a wide range, a certain very repeatable KVCO. What you'll probably get is something like the black curve. Okay, so that is something to know. The other thing was this guy, Kunal, I think pointed out in class, right? So of course, so this should actually be I1 over V0. Shouldn't be I1 over V1. I got confused because I think later for the other oscillator we started using V1. That should actually be V0. Okay, all of those numbers should actually be V0 because V0 cos omega naught t is the signal we are assuming at the gate, and we are also assuming that C1 is large and V1 is fairly flat, so that as far as signal is concerned, it's almost like a ground. Okay, so the overall V0 appears across the gate source. Okay. So what is phase noise? So what do we know about the oscillator? So first of all, we know that so far as we have seen, the oscillator has no phase restoring circuit. Okay, so it's completely autonomous. Okay, there is nothing to set the output phase. So what ideal oscillator you want? This is what you want from an ideal oscillator. What you actually get V0 of t cos omega naught of t plus phi of t. So this is here. So you have noise in the amplitude and noise in the phase. Okay. So if you actually plot the overall phase of the oscillator as a function of time, well, for the ideal oscillator, it's going to look like this because the total phase is just omega naught t, right? If you take a real oscillator, you're going to get something like this. Okay, because the phi of t noise is going to change the phase as a function of time. Now what is the instantaneous frequency? Omega naught plus d phi by dt. Okay, so what that means is, if you look at the spectrum of the oscillator, for an ideal oscillator you just have this. Okay, for an actual oscillator you are going to get what are called noise sidebands or noise skirts. Okay, this is what a real oscillator is going to look like, the spectrum. Okay, if you look at it in the time domain, so the ideal oscillator, let's say it's a sinusoid, what's going to happen is, as far as the phase noise is concerned, it's going to change the zero crossings. So that also manifests as jitter in the time domain. In the time domain, if you have variation in the zero crossing, that's called jitter. Okay. Okay. Now, if you look at the single sideband phase noise, actually I don't need this. Okay, so the definition of phase noise is, so let's say this is some f naught, and you look at a 1 Hertz bandwidth. Okay, at an offset delta f from the center frequency. So let's say the nominal frequency was f naught. Okay, you know your phi of t is going to cause noise on the sidebands. Okay, you're going to define the single sideband noise as a ratio of the power spectral density at an offset delta f, that is the noise power in a 1 Hertz bandwidth at an offset delta f from f naught. Okay, and you're going to take the ratio of that to the power at f naught, which is the carrier power. Okay. So this is the definition of the single sideband phase noise. Okay, and it's represented in dBc per hertz. Okay, it's dB obviously because you're taking 10 log and you're taking it with respect to the carrier power PS. So it's dBc. Okay, and of course the power spectral density. Okay. What are the effects of phase noise? Yeah, this delta f.
Depending on the delta f, your noise value is going to change.
Okay.
Standards. Why should I report this phase noise? What should be the value of delta f?
You would report delta f at different offsets. Okay. So obviously, like you have shown, if you choose a very close offset, the noise level is going to be high. If you choose a far off offset, noise level is going to be low. There's no doubt about that. So what the delta f which you report depends on your application. Okay. You'll see when you see the effects of phase noise, right? You'll see how it affects the receiver, and then you will get an idea of what you want to specify. Okay. So one of them is called reciprocal mixing. Okay. So let's say you have a large interferer, okay, and you have your desired signal which you want to receive, and you send that through a okay. In the ideal case, we saw that what you get at the output is, let's say this is the IF, and you get something close to that. Okay. Now, if you have noise sidebands around this guy, what you're actually going to get is this. It's a very bad figure, but and you're also going to get noise sidebands around the IF. Okay, you're effectively multiplying by a noisy LO. So in other words, if the interferer is large enough and the phase noise sidebands are large enough, you could actually drown your, or at least definitely desensitize your receiver. Okay. What else? So let's say you have a very strong TX. Okay, and your receive band is very close to it. Okay, it need not be your own it could be your own transmitter, it could be somebody else's transmitter. So in the previous case we looked at the phase noise effect on the receiver. If you look at phase noise effect on the transmitter, so this is going to have sidebands like this. Okay, So let's say if you take a full duplex system where you are trying to receive and transmit at the same time, the phase noise of the transmitter, if the power is large enough, is going to affect your receiver sensitivity. Okay. And it need not be the transmitter in the same system. It could be if somebody is trying to make a phone call or something right next to you. He could have a very powerful TX, so it doesn't have to be in the same system. It can be something nearby. And then if you look at OFDM, remember we talked about OFDM splitting the signal into a bunch of subcarriers. Okay, so what will happen is, so if you multiply it with the noisy yellow, what you will get at the output, and you will get what is called, you will get some noise from, due to the phase noise, you will get mixing of the carriers, subcarriers. Okay, you get what is called inter-carrier interference. Okay, so you can have all of these effects in transmitters and receivers. Sure, of course, yes. So the assumption is, okay, so what will happen is this, in a PLL, right, typically depending on the bandwidth, the close-in noise will get attenuated, and that is what you want anyways. Okay, you definitely want to get rid of the close-in noise, but the far out noise from the VCO does not get attenuated in a PLL, so that will definitely manifest as phase error, okay, as integrated phase error in your PLL. And if you look at your actual phase noise of an oscillator, you will see it actually looks something like this. It's going to look something like this if you plot it as a okay, if you plot the phase noise as a function of delta f, it has three regions, three major regions. Okay, so the first region has a slope of, goes as 1 by delta f cubed. Okay, so which means it has a slope of minus 60 dB per decade. The next region has a 1 over delta f squared. And of course you have a flat region. Okay, any real oscillator you take has all these three regions. Okay, sorry. Okay, and this point where it transitions from 1 over f cube to 1 over f squared is called the 1 over f cube noise corner. If you remember from your analog circuits, when you have flicker noise and thermal noise, that corner is called the 1 over f noise corner, right, the flicker noise corner. Similarly, you can define a 1 over f cube noise corner for the VCO. Okay, so what we'll look at, we'll look at three different kinds of noise models. The first one we'll look at it in detail because it's easy to analyze. For the class it's suitable. Okay, the other two are more sophisticated. We'll just quickly, in a few words I'll just go through them. If you're more interested, you can go ahead and read up the papers, but it won't be suitable for a first level class. Okay, irrespective of the architecture, any oscillator will have these three regions. Okay, whether it's LC oscillator or ring oscillator or relaxation oscillator or a crystal based oscillator, whatever you have, it will have all of these regions. Okay, what we'll do is we'll find out the reason for all of these regions. At least we'll look at some of the reasons why it could be caused. But the fundamental thing you should know is, actually we'll come to it. We are going to come to it now. So let's not jump the gun. So we'll just look at this. So the primary reference, for I guess the most used reference in phase noise theory is probably Leeson's paper. It's a classic paper from 1966. It's called a simple model of feedback oscillator noise spectrum. Okay. So what he does is he assumes that the we discussed the Colpitt's oscillator, where you assume there is a basic feedback through a capacitor and so on. Okay. So traditional oscillators used to be built as feedback systems. So what he does is he analyzes the feedback the system as an LTI system. So it's linear as well as time invariant. Okay, and then he assumes that the noise comes only from the tank resistance, the inductor resistance. Okay, and then he finds out you can find out the impedance of the tank, you can find out the noise and phase noise. Okay, and then of course it still doesn't explain the existence of some other regions in the noise curve. So he accommodates for that using some empirical factors. Okay. So what we are going to do is so what we are going to assume is we are going to assume that the noise comes only from RP. So in other words, so you have a noise source in parallel with the tank. We are going to assume to first order that the active circuit is noiseless, and of course it's a negative resistance, let's assume. Okay. Okay. So the current noise is 4 kTg. So what we'll do is the procedure we are going to adopt, find out the impedance of the tank at an offset delta omega, okay, from omega naught, find out the impedance of the tank, multiply this current by the impedance to find the voltage noise. Okay. So let's assume at a small offset omega naught plus delta omega, what is the admittance? So you have G, okay, this is your admittance. Okay, so we'll simplify this. Okay, and then you can expand omega naught plus delta omega the whole squared you're going to do the usual things. We've actually done this before. If you remember, when we did impedance matching for an LC resonant circuit, we actually found out the impedance. You remember this? It was 2 RC. Remember that the bandwidth was 2 RC, right? And that's how we found out the Q of the, like you said, yeah. So it's going to be similar, almost the same, okay? So again, you expand this, omega naught squared LC is 1, so you cancel off omega naught squared LC and 1. You neglect delta omega squared, right? You do the usual things. You'll end up with G plus okay, end up with something like this. Z of omega naught plus delta omega is just 1 over this. Okay. You can take out 1 over G as a common factor. Okay. You go down. Okay, so we also know Q is omega naught RC for the tank. Okay. One over G is R. Okay. This is the impedance of the tank. What is the magnitude? You can show that. You can simplify it. You have to do, 1 over root of square root of this guy, right? This plus this squared, right? What is 1 over a plus jb? You can do 1 over root of a squared plus b squared, and then since b is small, delta omega is small, you can do half instead of 1 plus x whole power n. So the usual thing, you get r omega naught by 2q delta omega. Okay. So your Vn squared over delta f is nothing but In squared over delta f times mod z squared. Let's do it this way. So it's 4 kTr times omega naught over 2q delta omega the whole squared. Okay, so that's the expression for your noise, the voltage noise. Okay, now you can also show, so there's a theorem in thermodynamics which says if you have noise, okay, and of course it's usually proportional to kT, right? So if you have such a noise, it usually splits equally between the amplitude and the phase. So there's an equipartition theory which claims that the noise is distributed equally, okay, which means the actual phase noise, let's not call it phase noise because that has a, so let's say, so the noise in the phase, so the noise in the phase, yes. No, it's just RP. This is steady state. You are doing a steady state analysis. Want what? What want split? you are talking about the noise between splitting between these two guys. Actually, okay, you're right, and the queue you're looking at is actually the loaded queue. Okay, you have to be a little bit careful. So what you're saying is right. However, you are just assuming that this is actually a no, input impedance is not high. Actually, it is actually very low and is negative. Okay, what you're assuming is this. Okay, you're assuming that the at an offset delta omega, okay, it may not cancel perfectly. So what you actually get is a very high Q once it's cancelled. The effective Q for a small signal is very high. Okay, so you are right in that sense that you have to assume the current is splitting. But if you assume that the Q is very high, it actually does split, flow mainly through the tank. Okay.
So minus R is the incremental impedance.
Minus R is incremental impedance. Yeah, all even this is incremental impedance, right?
No, RB is the like actual impedance, not incremental.
I mean, yeah, which is also the incremental impedance. So we are actually assuming a small signal analysis.
Yes.
Right?
So when you consider the noise, minus R will come into picture only if you deviate from F naught as slightly, then only the minus R, the incremental impedance comes into picture at that point.
Why the incremental is not? It's just the AC resistance, right? It's just the AC impedance,
Yes.
not necessarily for incremental with respect to delta omega.
No, at omega you find the incremental resistance.
Right.
That is going to vary with delta omega, right?
The incremental impedance will vary. Yes, it could vary. It could vary. There will be some variation. Probably not a lot.
So we are ignoring that.
Yes, we are ignoring that. Okay. So the actual noise in the phase is half of this, which is omega naught by 2q delta omega the whole squared. Okay.
So that means minus R will not have any impact.
Minus R will not have any impact. At least we are assuming it won't have any impact. Okay. Oh, this one. Yes. This result is because of the equipartition theorem. Yes. Yes. It's the phase. It's the noise in the phase. Okay. In that case, there the phi of t is dimensionless, right? It only has radians. Okay. In this case, you are assuming that the noise is still found as in terms of voltage. At the end of the day, you want it in terms of physical quantities, which is in terms of voltage.
So is it like for that fluctuation phase, if I compute the spectrum of
Exactly, that's right. So for that fluctuation in phase, you have to calculate the overall V of t, and then that gives you your the sideband value in terms of volts. Okay. Okay. So your phase noise is 10 log 10 2 kTr delta f. Oops, 2 kTr okay, so that's the noise in the phase over the signal power. Okay. Oops. Um, so what does it look like? So you have a 40 dB per decade. Right? But we know that a real oscillator has other regions. Okay? So what you are going to do is, he puts in two empirical parameters. Okay? So if you look at, so he puts in two other empirical parameters. So one is an empirical parameter called f, which is the device excess noise number. He calls it the device excess noise number. Okay, so that stands for the excess noise, first of all, primarily from the device, from the active devices. Okay. The other thing, it doesn't account for the 1 over f cubed region. Okay. Sorry. Yeah. So he also adds a dependence on a term called delta omega 1 over f cubed. Okay, which is the 1 over f cubed noise, which represents the 1 over f cubed noise corner. So both of these are empirical. Okay. So this was your original expression. Okay. He adds, multiplies it by the device excess noise number f. Okay, so what does this do? This actually gives you also a flat noise region. Okay, when you go far enough out, okay, it gives you a flat noise region, and then so he also adds a 1 plus, multiplies it by 1 plus delta omega 1 over f cube by delta omega. Okay. So if you take your plot your phase noise now, so you are going to get three distinct regions. First of all, so the first one is the noise corner is delta omega 1 over f cube. This noise corner is omega naught over 2 q. That's from this guy. Okay. And q is the loaded q. It's not the unloaded q. Okay.
So if I consider Q as the loaded Q, then G, should we consider that also as a loaded Q?
Definitely, yeah. The G will actually be loaded G. For example, if your if your buffer has some input impedance, that will figure in this. Okay. If your for example, if your transistors have some output impedance which is causing your Q to change, that may figure in this. There will be a number of things which figure in this. Okay.
So we we said G as 1 by RP.
Yeah. So in this case, it won't be RP just of the tank alone. It will be 1 by R of the of everything put together. Okay. So what all do we know? So Leeson's model. Accounts for all regions. So now he's built a model which can give you 1 over f cube, 1 over f squared and flat noise. So that is good. The other thing is it gives you some insight, some design insight also. So what does it tell you? For example, what happens when you double your frequency of the oscillator? Okay, so because there is an omega naught term, if you double the frequency, you know that especially in the thermal noise region of the phase noise, it's actually going to go up by 6 dB because it's omega naught squared proportional to 10 log 10 of omega naught squared. Yes. This one, because you have omega naught by 2 q delta omega the whole squared. It's proportional to 1 over delta omega squared. Oh yeah. Sorry, we are talking about okay. Sorry, have I kept saying 60 and 40 and okay, big mistake. Sorry, you're right. That's a big mistake. That should be 30, 20 and 0. Good. Thanks for catching that. Where did I? Definitely, that's a good catch. Thanks. Yeah, that's a good catch. Okay, so it tells you that if you double the frequency, the noise of in the thermal noise region is going to go up by 6 dB. Okay, so that it tells you. What else does it tell you? If you increase the oscillation amplitude, for example, okay, your P sig is proportional to V naught squared. Okay, again, so if you double the amplitude, your phase noise is going to go down by 6 dB. So those are all very good things. It gives you insight. So what you need to do as far as design, you need to maximize your signal amplitude. Okay, of course omega naught you can't do much about it, but for example you need to maximize Q. Okay, so obviously and it also tells you if you double your Q what happens to your noise, or if you double your amplitude what happens to noise. Okay, but it doesn't tell you anything about F. Okay, so it's a completely empirical factor. So if you really want to know what F is, design the oscillator, test it, make it, build it, test it, and then you know what F is. Okay, similarly about delta omega, delta omega 1 over F cubed. It's the same thing. And finally, we know that oscillators are nonlinear because you are relying on the nonlinearity to actually limit the oscillations, for example. Okay, and definitely the signals are large enough such that you can no longer use a small signal linear model for the transistor. Okay, and if you see even the Colpitt's oscillator which relies on feedback, the current is actually in terms of pulses. So definitely it's not a very linear system. Okay. The other thing, the oscillator is actually a time variant system as far as noise is concerned. Okay, so we know that this model falls short in several ways. Okay. So other models are the Hajime-Lee model. So what this does is it actually creates a linear time variant model for noise. The reason is, as far as the noise is concerned, the noise is actually a small signal. Okay, so what you can do is you can actually build a large signal model of the oscillator itself, but then assume linearization as far as noise itself is concerned. Okay, so linearity is quite valid. However, what is more important is that time invariance is not valid. So it's actually a time variant system. So one of the ways they explain it is, so let's take the signal, the VCO signal. Okay. So if you assume some noise is injected here, let's say at the peaks, what happens to the oscillator output? So it actually goes up here. So what happens is, any noise which is injected right at the peak, okay, what happens is the oscillator amplitude actually changes, but the zero crossing, nothing happens to the zero crossing. Okay. However, if you assume that there is some noise injected right at the zero crossing, what happens? So now your time is shifted, zero crossing is shifted, there is nothing in the oscillator to restore the phase, so it keeps oscillating at the new phase. Okay, so this itself shows, the simple model itself shows that as far as noise is concerned, the system is actually time variant because it depends on when you inject the noise. Okay. So what they build is, they build the noise theory around something called the impulse sensitivity function. Okay, they are represented by gamma. Okay, so the main idea is this impulse sensitivity function ISF, it encodes some information about the sensitivity of the oscillator itself. Okay, so it's very sensitive to the circuit topology. So different topologies will have different ISFs. Okay, so all it does is, for example, there are some cases where noise maybe, there are some oscillators, if you look at the cross coupled oscillator, the noise is actually injected right at the zero crossings, right at this point. Okay, so it is actually quite sensitive to the, as far as noise is concerned. Whereas if you look at the Colpitts, if you remember the Colpitts model we looked at, remember that the device actually turns on right at the peak of the amplitude. Okay, so which means that if the device injects any noise, it is actually fairly insensitive, as the phase noise is fairly insensitive. Okay, let's call this model 2. So it's, I mean, you don't need to know too many details right now in this class about this, but the main idea is, so if you have any circuit, you can actually calculate, you can, inject different impulses and find out how the oscillator responds and find out the ISF and calculate the noise based on that. Okay, and if you see, most of many simulators actually use this method because it's a fairly accurate method for calculating the noise. So the reference to the paper is actually there in the notes, which I'll post in class. Okay, I don't want to write out everything. So the other model is called the Rayl-Abidi model. Okay. So what this does is, this goes the other way. Okay, so this assumes that the oscillator is non-linear but time invariant. Okay, the main idea of doing that is they end up calculating an expression for f. Okay, because the Leeson's model started off with LTI system. What they do is they extend it to a nonlinear system and then calculate f. Okay, so f is 1 plus 8 gamma so this is the expression they come up with for f. Okay, so this is a somewhat more physical model. Okay, it's slightly more intuitive. It's probably easier to understand than the mathematical model. The previous model, the ISF based model, is fairly mathematical. Okay, whereas this one is a little bit, at least from a transistor point of view, is a little bit easier to understand. V naught is the amplitude. Okay, IT is the tail current, R is the resistance of the tank. Okay, and this is also nice because it actually gives you more insights. So your Leeson's model gave you some insights. This one gives you a little bit more insight. So for example, you can see what will happen when you change your current keeping your GM constant. Okay, so what happens if you change your current keeping the GM constant? Your overall F stays somewhat constant, but your amplitude actually goes up of the tank. If you increase current and keep GM constant, the tank amplitude goes up, F remains more or less the same. So what happens is, if you look at your Leeson's model, it still tells you what happens, because even though F stays the same, you have a P sig term here, so it will still get better by 6 dB. Okay, it also tells you that there is an optimum. So what happens is, if you keep increasing the current, what happens? So your model of your remember if you take a cross coupled oscillator, we found that the amplitude is actually 2 by pi IT times R. Okay, but if you keep increasing your IT, at some point of time your supply rails will limit your amplitude. Okay, at that stage what will happen is your V naught stays constant, but your F will start increasing. Okay, if you just keep increasing the current. Okay, so let's stop here and we'll continue next class. Okay, so next class we don't have much more on the VCO itself. We'll just go through a basic, in 10 minutes we'll go through a very basic VCO design procedure, what you need to do. Okay, and then we'll probably move on to other things. Okay, see you guys on Friday. Yes.
How do you